Hello everyone. In this video, we'll be seeing the second most important discrete probability distribution, that is Poisson distribution. Okay. So Poisson distribution, it is also a discrete probability distribution. Note that this is counting the number of events. Okay, the probability that a given number of events occurs in a fixed time interval or fixed space. Okay, so any number of events may occur in the given period of time. So this time period is fixed. In that time period, we are going to calculate the probability a given number of events may occur. Okay, here the occurrence should be of known constant rate, and this occurrence should be independent of the previous one. So for example, we are going to calculate the number of typos per page in a book. So this per page is our space. Within this space, we are going to find the number of typos. Number of events is nothing but event represents typos. And the number of phone calls received at a call center per minute. So this per minute represents the time interval. So among this time interval, we are going to record the number of phone calls received and the number of accidents at an intersection in a day. So at an intersection is a specified space, and also in a day represents the specified time. Both specification is given in this one. We are going to calculate the number of accidents. So we cannot fix the value. Only 10 accidents will happen in this day at this time. Okay, we cannot fix that. That can go up to any number. So this Poisson distribution, its parameter, that is x value, it cannot end with any finite value. For example, there may be no typos in that page. So 0 is possible. 1 typos may be there, 2 typos may be there, 3 typos may be there. So similarly, we cannot tell one upper bound for the number of typos in that book. So like that, in that call center, no call can be arrived in that particular day. So or in that particular minute. So starting from 0, n number of calls can be received at that call center. So the upper bound will not be there for Poisson distribution. So similar to previous lecture, here also we have to define the probability mass function of binomial distribution. A random variable x, it is said to follow a Poisson distribution with parameter lambda greater than 0 if its PMF function is given by lambda power x e power minus lambda divided by x factorial. So note that the parameter of Poisson distribution will be lambda, and x varies from 0, 1 to etc. So Poisson is an approximation of binomial distribution. It is very important. In binomial distribution, whenever the number of trial n is large, see if the n value is small, then we will be able to calculate the probability. But if the n value is large, calculating that probability will be very tedious. Similarly, the probability of success, if it is small, then in that case also finding the probability using binomial distribution will be difficult. So what we are doing is, the mean value of binomial distribution NP will be equated to the parameter of Poisson distribution lambda. And mathematically, if x follows binomial distribution with parameter n and p, and as n tends to infinity, that is very large, and p tends to infinity 0, that is very small, such that lambda equal to np, it should remain. Okay, it remains for all values of n and p. Then we can see Poisson distribution as a limiting case, that is limiting case of binomial distribution. Okay. So similar to previous one, we are going to find the MGF of Poisson distribution also. MGF formula is nothing but mx of t is equal to e of e power tx, and this can be written as summation e power tx into p of x, and x varies from 0 to infinity. P of x value is nothing but lambda power x e power minus lambda divided by x factorial. So since e power minus lambda is independent of the summation variable x, we can take this outside. So e power minus lambda into summation x equal to 0 to infinity, we can take x power commonly outside. So lambda e power t power x divided by x factorial, and note that summation x power or summation x power n divided by n factorial, this can be written as e power x, n is equal to 0 to infinity. So here in the place of x, we are having lambda e power t, and in the place of n we are having x. So if we replace this one, we will be getting e power lambda e power t. So our MGF function is e power minus lambda into e power lambda e power t. So since base is same, we can add the powers, and if we take lambda commonly outside, we will be getting e power lambda into e power t minus 1. This is our MGF function. And next one, using this MGF function, we are going to find the mean and variance value. E of x value is nothing but mx dash of 0. Already we have seen that it is e power lambda into e power t minus 1. We are going to differentiate this one, or we can keep the mx term as it is. That is e power minus lambda into e power lambda e power t. So if we differentiate that term, we will be getting lambda e power t into e power lambda into e power t minus 1. Okay. Now what we are going to do is, substituting x equal to 0, we will be getting lambda as our answer. So the mean value of Poisson distribution is lambda, the parameter itself. Next one, we are going to find the variance. The formula is same, e of x square minus e of x the whole square. We are going to find mx double dash. So finding mx double dash, it leads to lambda e power t, e power lambda into e power t minus 1 into 1 plus lambda e power t. If you substitute 0 in the place of t, we will be getting lambda into 1 plus lambda. So e of x square is lambda into 1 plus lambda. Variance is nothing but this term minus e of x, that is lambda square. So the leading value will be lambda. So the Poisson distribution is the only distribution which has equal mean and variance. So the mean value and variance value of this Poisson distribution is same, and that value is equal to lambda. Thank you.